Good morning, everyone. I'm Harini JS along with my teammate Yashvanth Kumar D. We are here to present our Embedded System Internships project at Emertxe. We have implemented a washing machine simulation using the PIC16F877A microcontroller. Over the next 20-30 minutes, we'll take you through how we combine theory and simulation to understand our embedded systems design practicality. The objective of this internship was to build a strong foundation in embedded systems by working on a hands-on microcontroller based project. We used MPLAB IDE for code development, Emertxe as a cross compiler, and PICSimLab for hardware simulation. Throughout the project, we learned real-time signal handling, embedded C coding, register level programming, and how hardware software components interact.
I will be walking you through the logic and code explanation part of our project. For this washing machine simulation, we wrote everything in C, which is the most common language used in embedded system because C lets us control directly hardware directly. It helps us read ports, write to output pins, and manage timing and more. We use several basic and modified data types throughout the project. Types like int, char, and float are common, while modifier like unsigned or long help fine-tune memory usage. For embedded system, qualifiers like const and volatile are especially important. For example, volatile is used when accessing ports like port B because the value may change outside the control of our code. In regular C programming, we use printf to display output and scanf to input. But in embedded system, we don't have any console. Instead of printf, we use functions like CLCD print to send output to the LCD display, and instead of scanf, we read input from switches and ports using port B or helper functions like read digital keypad. We also use the size of operator to determine the size of the data types in bytes. This helps us to optimize memory usage, especially in important embedded systems. A size t keyword is an unsigned integer type returned by sizeof. Embedded systems often rely on unsigned int or signed character for compact storage. Using the right modifier helps reduce memory usage and prevents error during operations like timer overflow or pin counting. We used if else and switch case statements to handle different conditions like checking switch states, selecting washing programs, or activating the buzzers. Switch case was especially used to program selection. Control flow is the backbone of our state machine logic. The while loop forms the super loop in our embedded program. We used for loops for delay generation or state counters and control statements like break or continue to exit loops or skip certain iteration. Each loop is carefully structured to ensure real-time performance. C has various operators we use frequently, like arithmetic operator, addition, subtraction, multiplication, division, and modulus. Relational operators like equal to, not equal to, greater than or lesser than or equal to, etc. Logical operators like and, or not, and most importantly for embedded work, bitwise operators. We always have to consider overflow and underflow in data. For example, character can hold only up to 127, so going beyond warps around. We also used arrays for storing program names, water levels, and more. Array makes easier to scroll through the displays options on the CLCD.
An embedded system is a combination of hardware and software designed to perform a dedicated function. A simulation represents a standalone system that doesn't depend on any external computing system. It also behaves like a real-time system where timing is crucial, especially in operations like water level selection, washing cycles, and pausing, resuming the process. Key components include processing unit, microcontrollers like PIC16F877A, memory, RAM which is volatile, ROM which is non-volatile, and EEPROM and flash. Input-output ports allow communication with external peripherals like switches, LEDs, and displays. Understanding each component's role helped us design our system logically and efficiently. Unlike microprocessors, microcontrollers like PIC16F877A integrates CPU, memory, input-output ports, and timers all in one chip. It uses the Harvard architecture, which separates instruction and data memory to allow simultaneous access, thus speeding up execution. We wrote our code in MPLAB IDE, compiled it using the XC8 cross compiler, and simulated it in PICSimLab. PICSimLab mimicked real board hardware and helped us test our code visually. The specific board used was PICGenius, and we used the board schematic to locate pin mappings for LED, switches, CLCD, buzzer, and fan. We refer to the datasheet of PIC16F877A to identify that ports B and D were connected to LEDs. Using tris_b equal to 0x00, we configured port B as out. Each port has a data direction register, tris, that determines whether pin acts as input 1 or output 0. We used header files to simplify configurations with macros. Each of the 8 pins of port B is connected to an LED. In current sourcing mode, setting a pin high sources current through the LED, lighting it up. We use software delays, loops to control the rate of blinking. LEDs on simulation behave like actual hardware based on GPIO state. The digital keypad uses tactile switches connected to RB0 to RB5. To ensure we don't modify RB6 and RB7, which are LED outputs, we use tris_b is equal to tris_b or 0x3f. This ensures only the lower 6 bits are set as inputs. We also studied edge versus level triggering. Edge triggering is for toggling once per press, while level triggering keeps toggling as long as the button is held. We use timer 2, an 8-bit timer, to generate periodic interrupts. At 20 MHz, one instruction cycle is 0.2 microsecond. So, 256 ticks take 51.2 microseconds. To get a 1 second delay, we preloaded timer 2 to start at 6 and use PR2 equal to 250, repeating the overflow 20,000 times inside the ISR. The ISR toggled LEDs every 1 second. An embedded system combines hardware and software to do a specific task. Types include standalone systems like washing machines, network systems like smart home devices, real-time systems like car airbags, mobile systems like smartwatches. An embedded system has a processing unit like a microcontroller, RAM for temporary memory, ROM for permanent memory, EEPROM or flash for both. Each type of memory has a specific purpose in the system. Microcontrollers have everything: CPU, memory, input-output in one chip. They are used in simple, dedicated devices. Microprocessors need external parts and are used in complex systems like computers. Microcontrollers often use Harvard architecture, which speeds up data access. For this internship, I used MPLAB IDE to write and edit code, XC8 compiler to convert code to machine language, PICSimLab to simulate hardware like the PIC16F877A microcontroller. LEDs are controlled using microcontroller ports. Tris registers decide whether a pin is input or output. It is called data direction register. Port registers send on or off signal to LEDs. A simple program turns LED on and off with a delay to make them blink. A typical embedded system C program must consist of bare metal code which directly interacts with the hardware, bypassing any operating systems or abstraction layers. In embedded system, every .c file must have corresponding .h file, and any program that is going to be taking place must be running inside an infinite while loop. Keypads are made of rows and columns of switches. When a key is pressed, it connects a row to a column. Bouncing happens when a key press creates multiple signals. Debouncing is used to filter those extra signals. Triggering can be level placed while pressed or edge based on press. We can control LED patterns using keypad switches. Switch 1 blinks all LEDs, switch 2 blinks alternate LEDs, switch 3 blinks left and right halves. Each pattern uses bitwise values to set the LEDs. This is a common program for both level and edge triggering. Only RB0 to RB5 are switches. RB6 and RB7 are just LEDs. For the switches to be input, we assign the value 1. But RB6 and RB7 cannot be assigned values as input or output. Therefore, retain the same value x that it exists in x can be 0 or 1. For this, we use bitwise OR operator given as trisb is equal to trisb bitwise OR 0x3f. This program does blink all LEDs on port D when switch 1 is pressed, blink alternate LEDs on port D when switch 2 is pressed, blink nibbles first 4 and last 4 on port D when switch 3 is pressed. For alternate LEDs to blink, first the 8 LEDs are 0xAA. Next, the 8 LEDs are 0x55. For nibbles to blink, first the 8 LEDs are 0xF0. The next 8 LEDs are 0x0f. An interrupt is a communication process set up in a microprocessor in which an internal or external device requests the MPU to stop the processing. The MPU acknowledges the request, attends to the request is like a timer, resumes its processing as usual. The source of interrupt could be external or internal. Interrupts can be classified as hardware and software. Timers help track time, create delays, and schedule tasks. Each tick increases a counter. When the counter reaches the limit, it overflows and can trigger an interrupt. Timers are useful for making actions happen at regular intervals, like blinking an LED every second. Prescalers and postscalers adjust how fast or how often the timer works. Prescalers slows down the timer. Postscaler changes how often an overflow triggers an interrupt. This helps create longer delays like 1 second from a fast clock signal. CLCDs show characters like names, numbers, or messages. They use control lines and data lines to work. To display text, we use functions like CLCD_print and CLCD_put character. CLCD_put character is for single characters, while CLCD_print is for strings. Delays are used to give the LCD time to process each command. Buzzers and fans are controlled using digital output pins. We set a pin high to turn on a buzzer or a fan, and low to turn it off. They are often used for alerts or status signals in process. In our project, we'll use buzzers to indicate that the washing machine door is open. We created a simulation of washing machine using PIC16F877A. It uses a CLCD to show messages, a keypad to select programs and levels, timers to count time, a buzzer and fan for alerts, door sensor simulation for safety. It supports start, pause, and resume features. Initially, the washing machine displays powering on screen. The microcontroller starts in the idle state after reset. The CLCD displays a welcome or standby screen. At this point, the system continuously checks for switch 5 button. Once switch 5 is pressed, the machine transitions to the next state. After detecting switch 5, the screen displays a brief startup animation or confirmation message. A timer is used to delay the transition. After this delay, the system moves to washing machine program screen. The washing program screen now displays the first of 12 washing programs. Switch 4 is used to scroll through the list. Each press of switch 4 loads the next program in sequence. A long press of switch 4 confirms the selected program. Once confirmed, the system proceeds to the water level screen. The water level is differentiated such as low, medium and high. Again, switch 4 scrolls through the options. A long press selects the desired level. After selecting water level, the CLCD displays the start screen. Switch 5 is used to start the washing cycle. Switch 6 is used to stop or pause operation at any point. Until switch 5 is pressed, the machine remains idle in the screen. Once started, the screen displays current stage. It also shows a countdown timer indicating time left in that stage. A timer interrupt is used to decrement time accurately. Each stage transitions occur automatically based on countdown. After spin is completed, the machine displays washing complete. The fan is turned off automatically. The buzzer turns on briefly to notify user and then turns off. At any time during washing, if the door is opened, the machine halts. The CLCD shows door open warning. The fan turns off. The buzzer turns on and stays on until the door is closed. Once the door is closed, the operation resumes from where it left off.
This is the demo of washing machine simulation project developed using PIC16F877A microcontroller as a part of my internship. Let me show you the working of the project step by step. As you can see, when the system is powered on, the CLCD displays press key 5 to power on the washing machine. Now I press key 5 to power on the washing machine. The message changes to powering on this washing machine screen. Once powered on, the system navigates to washing machine program screen. We can choose various washing modes like daily, heavy, delicates, whites, stain wash, eco cottons, woolens, etc. We scroll through the options using switch 4. A long press on switch 4 selects the highlighter program. Like here, I will select heavy. Next, the system goes to the water level screen. Available levels are auto, low, medium, high, max. Again here we use switch 4 to scroll and long press to select. Let's choose medium for this demo. Now we are on start screen. The CLCD prompts switch 5 to start and switch 6 to stop. Pressing switch 5 will start the machine with the selected program on the water level. Pressing switch 6 will take us back to the program selection. Here, I'll press switch 5. After starting, the machine displays the current function and the time remaining. It processes automatically to rinse and spin based on the selected mode and the timing. You can also press switch 6 to pause and switch 5 to resume. Now, if I press switch 1, which indicates the door is open, the system detects this and displays door is open, please close the door. Also the buzzer turns on for the safety indication. Once I release the switch 1, the door is closed, the buzzer turns off and the washing continues. After the washing cycle completes, the CLCD displays program completed, remove the cloths. This marks the full end of the washing cycle. Thank you for watching this demo.
Let's now walk through the complete washing machine simulation and explain each stage of operation. The system was implemented using Embedded C and simulated using PICSimLab with real-time response and feedback on the CLCD. First, we are able to see power on screen. The microcontroller starts in the idle state after reset. The CLCD displays Press key 5 to power on washing machine. At this point, the system continuously checks for switch 5, power button. Once switch 5 is pressed, the machine transitions to the next state. After detecting switch 5, the screen displays a brief startup animation. A timer is used to delay the transition. After this delay, the system moves to the washing program screen. The screen now displays the first of 12 washing programs. Switch 4 is used to scroll through the list. Each press of switch 4 loads the next program in sequence. A long press of switch 4 confirms the selected program. Once confirmed, the system proceeds to the water level screen. The user is presented with options such as auto, low, and medium. Again, switch 4 scrolls through the options. A long press selects the desired level. After selecting water level, the CLCD displays the start screen. Switch 5 is used to start the washing cycle. Switch 6 is used to stop or pause the operation at any point. Until the switch 5 is pressed, the machine remains idle in the screen. Once started, the screen displays the current stage. It also shows a countdown timer indicating time left in that stage. The entire cycle is divided as follows: wash 46% of total time, rinse 12% of total time, spin 42% of total time. A timer interrupt is used to decrement time accurately. Each stage transitions occurs automatically based on countdown. Now we can press switch 6 to pause the washing machine process. After that, if you need to start the process again, we can press switch 5. Now, to detect if the washing machine door is open or not, we use RB0 pin. Switch 1. At any time during the washing, if the door stimulated using switch 1 is opened, the machine halts. The CLCD shows door open warning. The fan turns off. The buzzer turns on and stays on until the door is closed. Once the door is closed, the operation resumes from where it left off. This simulation demonstrates the working of a real-time washing machine on a microcontroller, from user inputs and interface screens to timing, safety, interlocks, and function transitions. The project is a complete embedded system implemented in a modular and logical structure. This concludes the full project demonstration of a washing machine simulation project.
To finish my part of presentation, I want to share what I learned from this project and what I plan to do next in the field of embedded system. First, this project helped me clearly understood how different parts of microcontroller work together. I saw how we combine hardware and software to build useful things like our washing machine simulation. My goal is to build more advanced embedded projects. Finally, I want to improve my debugging skills to find and fix problems in my code more easily. Overall, the internship gave me a strong start to embedded system. It helped me build real-time application and boost my confidence to take on bigger projects in my future. Thank you.